Hello, in this video we're going to focus on projectiles. I'm going to start by explaining a little more about the resultant velocity of a projectile and how that comes from a combination of the horizontal component of velocity and the vertical component of the velocity. I'm then going to look at an equation of motion example involving projectiles. And I'll finish by explaining a little more about Newton's thought experiment, which really helps us to understand satellite motion. A cannonball is an example of a projectile, so let's have a look. So the arrow on that cannonball shows the direction of the resultant velocity. So I'm just going to play that again. And you can see how the magnitude and the direction of that resultant velocity changes during its journey. So we know already that a projectile consists of has two components to its velocity. It has a horizontal component, which is traveling at a constant velocity, and it has a vertical component which is accelerating due to the acceleration of gravity. So we can view those in this animation here. So you can see the constant horizontal velocity, and you can also see the vertical velocity. Initially, it decreases as it's moving upwards, and then it reaches zero at the maximum height, and then it increases as it's moving back down again. So let's have a look at that another twice. The combination of the horizontal and vertical components of velocity give us the resultant velocity at any particular moment in time. So it is not possible for a resultant velocity to be completely in the vertical direction. That's impossible because there's always a horizontal component to that velocity while the projectile is moving. However, there is a time when the resultant velocity is perfectly horizontal, and that would be at the maximum height when the vertical component of velocity is equal to zero. Let's have a look at question 4.5 from last week's questions. So a ball of mass 5.0 kilograms is thrown with a velocity of 40 meters per second at an angle of 30 degrees to the horizontal. So we can see that in the picture here. And we're trying to calculate four things. We want the vertical component of the initial velocity of the ball, the maximum vertical height reached by the ball, the time of flight for the whole trajectory, and the horizontal range of the ball. The range, as we can see from the diagram, is just another name for the horizontal distance or displacement in this situation. So, to tackle this problem, I find it helps me to draw the diagram first. So I've just drawn a little sketch of the situation here, although we do already have the diagram in this particular question, but some of the questions didn't include the diagram. We then have to, as normal, choose our positive directions. So I'm choosing up the way and to the right to be positive because that was the initial direction that the projectile was moving in. We then have to look at suvat for horizontal and vertical. So horizontally, we don't know the horizontal displacement. We're going to try and find that in part D. The initial horizontal component of velocity, we can find out by using V cos x. So 40 cos 30, which is 34.6. So I've added that in there. The final horizontal velocity just before the ball hits the ground will also be 34.6, and there's no acceleration horizontally as long as we ignore air resistance. We don't know the time of flight. We're trying to investigate that in part C. Vertically, we don't know the maximum height. We're trying to find that in part B. The initial vertical component of velocity is v sine x, which is 40 sine 30, which is 20 meters per second. V is 0 at the maximum height, and the acceleration would be negative minus 9.8 meters per second. So we've already answered part A. The vertical component of initial velocity of the ball was v sine x is 20 meters per second. We're now going to find the maximum vertical height reached by the ball. So to do that, we need to use the vertical components. Because we're trying to find the vertical height, we must use the vertical components to find that. So we can ignore the horizontal components completely and just focus on vertical. So to find S, we can use the equation v squared equals u squared plus 2as. I'm choosing that equation really because we don't know anything about t at the moment, so it makes sense to use that equation. Substitute the data and rearrange, we get a height of 20 metres. So the maximum vertical height is 20 metres. For part C, the time of flight for the whole trajectory. Time is the same both horizontally and vertically, so we have a choice to make here. We have to decide whether we can use the horizontal components or the vertical components to find time. In this situation, we can't use the horizontal components because we don't know the horizontal displacement. So we must use the vertical components for this particular example. Although other examples, it might have been better to use the horizontal components, but in this one we're forced into using the vertical components to find time. So we can use the vertical components and use the formula v equals u plus at, and that gives us a time to the maximum height. If we take v equal to 0, means it's 2 seconds for the ball to reach its maximum height. So that means if it takes 2 seconds to reach its maximum height, it means the total time of the flight for the whole trajectory would be 4 seconds. It's 2 seconds to the maximum height and then another 2 seconds to land. Finally, we're trying to find the horizontal range of the ball. So the horizontal range of the ball is really the same as the displacement. So we're using horizontal components this time. And we can use the equation S equals ut plus a half at squared. And that gives us a horizontal range of 140 meters to two significant figures. Sir Isaac Newton had a really good understanding of satellites, and this was well before satellites were a thing. Newton published some of his thoughts. He used to do thought experiments where he'd think things through without actually having the technology to be able to test them. And one of his famous thought experiments was to do with satellites, and this was published in 1687 in this book here, Principia Mathematica, which is one of the most famous scientific books of all time. So it's quite remarkable to think that this was 333 years ago that Isaac Newton understood about satellite motion. He'd never seen a satellite, there were no such thing as satellites, but he was able to think about his knowledge of projectiles and expand that to satellite motion. So in the next slide, I'm going to explain a little bit more about Newton's thought experiment. Isaac Newton imagined a cannonball being fired horizontally. So we know that a cannonball is an example of a projectile, so it travels horizontally with a constant velocity and it accelerates in the vertical direction. So let's have a look at that again. So the combination of those two velocities make the cannonball move in a curved path. So Isaac Newton imagined having a bigger cannon. So if we fire the larger cannon, we can see that the cannonball travels a further distance. It's got a larger horizontal speed, so it travels a further distance. We can also see that the Earth curves away, so this also allows the cannonball to travel a further distance. Isaac Newton imagined a bigger cannon yet, which could fire cannonballs with an even bigger horizontal velocity. So let's have a look at this example. So now the cannonball has such a high horizontal velocity that as it's falling back towards the Earth is curving away from it as well. So it now orbits the Earth and has become a satellite. So this is what a satellite is. A satellite is an example of a projectile which has a constant horizontal velocity but has an acceleration in the vertical direction. We've reached the end of this video. I hope it's helped to improve your understanding of projectiles. Thank you for watching. Bye for now.